Hello, this is going to be another analysis of David Weiss's Flat Earth Clock app. And in previous videos, I analyzed the sun's position and movement on his app. One thing that I noticed in those other videos is that when you look at where the sun is drawn on a daily basis, I noticed that the sun would start on the June solstice at the Tropic of Cancer or close to the Tropic of Cancer, and it would just creep along slowly until it got to the 21st or the 22nd of the next month, creep along, and then it would make a giant leap, and then it would continue to creep, and then it would make another giant leap a month later, continue to creep, and make another giant leap a month later. So that was the pattern. I wanted to get the computer to confirm what I saw and to produce an ephemeris of the sun's position in each of those frames, so that hopefully I could use the data to create a model and to add David Weiss's flat earth clock math to my own skywatching app. But that's going to be fodder for another upcoming video. For now, I just want to focus on how I got the computer to generate that ephemeris. And by the way, I'm going to make the data available, so check the description below. You should find links to 2 spreadsheets. I started off several months ago writing an application that tried to read the position of the needles in each of the frames to derive the time. But unfortunately, I noticed that in the fast time-lapse speed mode of his app, midnight does not correspond to midnight on the clock. Midnight corresponds to whatever the local time was when you changed speed from normal to those higher speeds. That's going to be fodder for another video as well. But I took that application and I just tweaked it, and I kind of ignored parts of what I did, and I just focused on trying to make that other part a little bit better. And so what I did was I went in 2 different passes. So the first pass, I looked at all of the pixels within a range of radii. So from about here to about here, I was looking for all of the pixels that were kind of this yellow color. Once I found those candidate pixels, I incremented a count in 2 different matrices. The first matrix represented the radius. So I essentially counted all of the pixels that were along a particular arc. The second matrix represented the angle. So everything between angle 0 and angle 0.9999, for example, were added in one cell of an array. Everything between 1.0 and 1.99999, for example, were added into a second cell of an array. And then by using those 2 arrays as a 2-dimensional matrix, I was able to identify the general area that was the most likely to be where the sun was. And it might have been over here, it might have been over here, it might have been in the middle. But then what I did was I focused on this area of the image, and then I made a second pass where I then focused on all the colors that appeared yellow like that. And I summed the radius of each of those pixels, and I summed the angle of each of those pixels in a separate variable. This is what it would have looked like as it went through identifying where the sun was. And then when I was done, I had a count of all of those pixels that were identified, and I had a sum total. I was able to compute an average radius and an average angle, and that is what I exported along with the frame number. So in this spreadsheet that I have, column A is the frame number, 55,000 or 53,000 or something like that. Column B is the average radius, and column C is the average angle for each of those pixels that were identified. The other spreadsheet is a copy of the NOAA Solar Calculations spreadsheet that is available online. I made another copy of what I had already, and I modified it to calculate the sun's position every hour for the entire year. And this graph represents the sun's subsolar latitude throughout the entire year. And as you can see, it starts off at around 23 23 degrees or thereabouts and goes down to minus 23 degrees 6 months later and then goes back up again to 23 degrees north again. It appears very smooth as one would expect. The Flat Earth Clock app does not look like that at all. The computer had identified the radius in pixels, but for convenience, I wanted to see what the equivalent latitude would have been. So if I use the measure tool in GIMP and I measure the radius from the North Pole to the equator, I'm going to get about 280 some degrees, but it's easier to measure the diameter, which is going to be 568-ish pixels. When I took my time to measure it, I got 284.1, which would have been the radius. Multiply that by 2. That would have been 568.2 pixels. If there are 284.1 pixels for 90 degrees on the AE map, I need to calculate the number of pixels from the subsolar latitude to the equator and multiply that by the pixels per degree to get me the total number of degrees. And so the way I calculated the latitude, I subtracted the radius that the computer identified from 284.1, multiply that by 90 degrees and divide that by my 284 pixels per 90 degrees, and that derived an equivalent latitude in degrees. I also calculate the longitude, which I don't really have to in this case because I'm not using it, but this is the formula that I'm using to take. That would be 0, 45, 90, 180, 270, all the way back to 360 degrees. So I'm taking that angular coordinate and turning it back into a longitude. I made a slight error in the spreadsheet. It's off by 15 degrees. This here is the prime meridian. That should be 90 degrees. This should be 75 degrees. This should be 60 degrees, not 75. And I went by my longitude, which was 75. That would have been this. This should be 30 degrees, not 15, to get the proper longitude. There was one other thing that I noticed when I was looking at where the sun was placed on the Flat Earth Clock app. The sun doesn't quite make it to the Tropic of Cancer in June, and in December, not only does it get to, but it overtakes the Tropic of Capricorn by quite a bit. I was kind of suspecting maybe they're trying to be cute and adding some sort of parallax to it. So I would have to compensate for whatever parallax they might be introducing. I've got a few ideas how I'm going to do that. But I also ended up calculating the minimum and maximum values of the radius along with the minimum and maximum values of latitude. The average, if there is parallax, then the average for the equator would be 300 pixels rather than 284. The proper obliquity is going to be 23.436 degrees. Multiply that by 2, so there should be a total deflection of the sun by 46.87 degrees of latitude throughout 6 months, and David Weiss's app has a total of 50 degrees. Unfortunately, it's still chugging away, but you can see that there were a couple of days that the computer has also identified where the sun was jumping into the wrong zone, if you will. This was in January. If I remember correctly, this was January 10th and this was January 18th. There were a couple of days in January where the sun was jumping for that day and then came back to where it was the rest of the month. This was in March, and whenever it finally gets over to here in July, it's going to jump one more time. The computer has identified all of the individual days where there's some kind of glitch in their algorithm that determines what band the sun should be in. I've also noticed that the slope doesn't appear to be the same from month to month. I suspect what they've done is they've taken 46 8.8 degrees, divide that by 12. So that would be 3.9 degrees per month. And so if they start on June 21st, they would take 3.9, and since June has 30 days, they would divide that by 30. I took a look at the slopes that you can see, and there are different slopes for different months. I'll try to figure out if there's some kind of usable pattern that can shed some light on how they calculate the sun's position on a daily basis like that, and why or how those slopes are different from month to month. But at this point, I think that I've got enough data that I can go ahead and approximate what he's doing in my own app. And once I perform a similar calculation to generate an equivalent latitude and longitude, I'll then be able to use the rest of the formulas that I have to convert it into an altitude azimuth. Then I'll be able to see how it should match what my security cameras capture on an ongoing basis. And I suspect that the outcome is going to be somewhat humorous. That's going to be it for now. Thank you for watching. If you like the video, I would appreciate the thumbs up, the subscribe, comment below, all that other good YouTube stuff. And with that, I'm going to see you again in another video soon enough. So bye for now.